Hello everyone, welcome to this episode. Today I'm talking with Chris Fields. Chris's work I will link. He has a website which itemizes or shows all of his work, which covers really, well, Chris's work covers, it's very eclectic. He has done work in the fields of cognitive science, quantum physics, quantum theory, biology, and I think, at least in my understanding and reading of Chris's work, and I think that comes through in this conversation, is Chris's work's unified by his interest in information processing and how systems can be understood as engaging in information exchange or sort of communication. And he's also done work and written papers on sort of philosophy and what is consciousness. And yeah, it's just very interesting, and I really enjoyed the conversation. So yeah, I hope you do. If you do, I'll be releasing more stuff in the future, so feel free to subscribe. That will help. But yeah, most importantly, enjoy.
What I've actually said is that the quantum theory doesn't actually have a measurement problem, which is the canonical philosophical problem with quantum theory. It's called the measurement problem. How do you get from a classical description to or how do you get from a quantum description to a classical description? And my position here is, and my approach to quantum theory is very much influenced by Chris Fuchs and the ideas that he introduced first as quantum Bayesianism and then as cubism, QB standing for quantum Bayesian. And he really emphasized that what observers are doing is actively probing the environment, and that when an observer receives an observational outcome, a classical piece of data, by acting on the environment, that classical piece of data is an action of the environment on the observer, or you can think of it as an action on the environment on the observer's instrumentation. And this view is itself very influenced by the work of John Wheeler, starting in the early 70s was my first exposure to this idea of Wheeler's, that the physical universe actually consists of observers, of information processing and information exchanging agents, and that physical dynamics is a process of communication. It's literally a process of communication. So I would say that what my thinking adds to cubism is the idea that systems themselves cannot be viewed as ontological, as given entities. That if some quantum system is making measurements of another quantum system, then the first measurements that are made are measurements that pick that quantum system of interest out from the background, and so distinguish it from everything else. And that's a very simple idea. I mean, if you're interacting with your laptop, then the first thing you've had to do is find your laptop and distinguish it from everything else in your office. So you did that by making measurements of its state. It's probably its size and shape and position and color and some of the stuff written on it and things like that. So you made all these measurements of part of the state of your laptop. And those parts of the state of your laptop are not the parts that you're interested in when you're using your laptop. So in physics language, they're not the pointer states, right? The pointer states named by analogy to an old dial that actually has a pointer. You're interested in what the pointer is pointing to. You're not interested in the color and shape of the dial. But you have to have those other measurements to know what the dial is, to distinguish the dial from your desk. So that's left out in most discussions of measurement in physics, this idea that observers have to actually identify the systems that they're observing. So that identification itself is a classical representation. So I don't represent my laptop as some sort of superposed state between, say, my laptop's degrees of freedom and my desk degrees of freedom. No, by observing it, I've actually fixed and then assumed or stipulated some particular classical state. And it's that collection of classical states that I regard as my laptop, as defining my laptop for me. So when one thinks that way, then it becomes clear that what quantum theory actually is a theory of measurement and action. So it's a theory that describes how one agent, me, for example, interacts with another agent, everything but me, or not me, or my environment. And if the first agent is a fairly cognitively complex system with a lot of computational power, then that first agent can kind of parse its environment into a bunch of different things, a bunch of different objects that it regards as persistent in time. And that's what's required to have an ontology, an in-practice ontology. And humans have those, and we talk about them with each other, and we take them for granted. But the first step of understanding measurement is to understand where that ontology came from and to see that the ontology itself is a result of our interactions with our environment. And those interactions are all two-way. So they're measurement of the environment and also preparation of the environment or action on the environment.
Right.
So I treat quantum theory as a theory of measurement, not a theory with a measurement problem. It tells us what we're doing when we're interacting with our environments.
Right. And then as that relates to, for example, the kind of classic example of which I've heard you use of like Alice and Bob, and how there's the kind of the difficulty of, or not difficulty, I think at times for people, the confusion of entanglement. And am I right in saying it's because they're essentially one system, whereas some people see it as that it's almost as though it's one is. Does that make sense or not?
Well, if a system is in an entangled state,
Mm-hmm.
that just means that its state can't be separated. It can't be factored into two independent states. So formally, if some composite system, call it AB for Alice and Bob, if Alice and Bob are entangled, then neither of them has their own individual independent state. So if we're going to talk about independent agents who are interacting within some shared environment, but who are interacting with that environment in a way so that Alice's interactions are separate from Bob's interactions, or distinct from Bob's interactions, then they have to be unentangled.
Right.
Because if they're entangled, they can't act independently. And separability, the lack of entanglement, is a very specific special state. The vast majority of quantum states are not separable. So in classical physics, we make this assumption that everything we see is separable, that we're dealing with a bunch of objects or particles, or call them what you want to, atoms, and they're each independent of all the others. And that's an extremely special assumption, right? You're building an enormous amount into making that assumption. And quantum theory just points out that that's a really highly unusual state. You're very unlikely to ever come across a state like that in nature.
I see. Yes, yeah. That's and then you've also done well, am I right in saying you've sort of found kinship between the sort of free energy principle, and then sort of giving it a kind of a quantum sort of account almost, and a sort of I don't know if equating is the right word, but with is it the holographic principle? So this kind of because what I suppose I'm thinking about here anyway, which I find interesting, is Markov blankets, or perhaps because of this sort of idea of measurement and sort of systems and agents sort of making measurements, is sort of the idea of Markov blankets, and then the holographic principle. So yeah, would you be able to sort of how would you say? Yeah, how is the free energy principle, or how can it inform an understanding of sort of measurement of systems making measurements, perhaps?
I may have lost you.
So did you hear me?
No.
Okay.
Repeat what you just said.
That's fine. So I was just, to be honest, it's probably a good thing, because I was sort of trying to find my words. But basically, so yeah, you've done work, I believe, or the sort of how the free energy principle, you've sort of found kinship or with the holographic principle. And I suppose both of these speak to, at least how I see it, is the idea of like Markov blankets, and how systems are sort of delineated in some sense from what they're not, and so how does the free energy principle and Markov blankets and sort of bear upon this idea of making measurements, I suppose?
Well, let's go back to what the free energy principle is about, right?
Mm-hmm.
The free energy principle is about a system that is able to maintain some sort of identity over time. So the free energy principle is basically a criterion for the way a system has to behave over time if it's going to maintain its identity, which means if it's going to maintain its distinction from its environment. And one can think of the distinction between a system and its environment in terms of a boundary. So we can wrap a boundary around the system and say, okay, this boundary is what distinguishes it from its environment. And so the free energy principle is basically a statement of how a system has to behave if it's going to maintain the integrity of its boundary. And when the FEP is stated in classical language, in the language of a causal network, then that boundary is very naturally represented as a Markov blanket. Markov blanket simply being a set of states in the joint system the universe that consists of the system you're interested in plus of its environment. There's some set of states in that universe that the system depends directly on. And it's those states that are the Markov blanket, and they separate it from its environment. So the free energy principle is really just about this distinction between a system and its environment. And when one formulates the FEP in terms of, in quantum theoretic terms, one again thinks of some universe in which the system is embedded. And one assigns a state space to that system in the same way that one does in the classical formulation. And then one just slices that state space someplace and says, okay, now the left side's the system, the right side's the environment. Now that slice is where you've drawn the boundary. And now you can ask, if I bound the system in this way, is it unentangled with its environment? So have I factored the state space of this universe by distinguishing system from environment in this way? And if I factored the state space, if I factored the state of the universe, and so I have system and environment having separate states or separable states in the technical language, then they're conditionally independent of each other. And it's conditional independence that a Markov blanket enforces or guarantees. So the two ways of thinking are really, other than adopting different formalisms, highly analogous, and you could almost say the same, in that in both cases, one's talking about under what conditions does the system remain separate from its environment, distinguishable from its environment. Ooh.
There we go. Sorry, Chris. This is what I mean. It does it once every time I speak to someone. I don't know what it is. It just has this habit of doing it. So I didn't hear you for the last sort of 20 seconds or so.
Well, I was saying that the approach taken in quantum theory and in the classical formulation of the free energy principle are up to the difference between the classical and quantum mathematics, the formalism. They're the same idea. It's how does the system have to behave in order to maintain its distinction from its environment? And in classical physics, one formulates that in terms of conditional statistical independence. And in quantum theory, one formulates it in terms of separability, so lack of entanglement. But the outcome of those, in both cases, is conditional statistical independence of its behavior. So if a system is conditionally statistically independent, one can regard it as having free choice of action. Its actions are not determined by its environment.
Yes. Yes, that makes sense. I'm curious because you've mentioned Wheeler, and this sort of participatory universe. And I think I heard you say, there's a sort of an assumption in classical physics, and I can't remember exactly the episode. I listened to you a bit where if you don't think this sounds right, please tell me. But I think you said in classical physics, there's almost an assumption that observers are like God. Does that sound make sense?
In classical physics, there's the assumption that observations can be arbitrarily precise. So what what would it mean to have an observation that was arbitrarily precise? So classical physics is all done using real numbers or complex numbers. So continuous fields, continuous space-time, for example. So each point in space-time is represented by a real number. So a number with infinite precision. So what would it mean for a measurement to be made with infinite precision? Well, infinite precision requires infinite energy. So one can think of it this way. If I want to completely isolate some system, say this is my cell phone. If I want to treat this object as completely isolated from the rest of the universe, when I interact with it, so that my actions on it are my actions and nothing else. Nothing else is relevant to this thing. Then I have to have the power to hold the entire rest of the universe at bay.
Yes, yeah.
To prevent it from affecting this object in any way, so that I can interact with it with infinite precision. So here's a practical example. If this thing is completely isolated, then I have to completely protect it from all cosmic rays. Right? They're cosmic rays all the time, penetrating us and everything around us. So this thing can't be isolated from cosmic rays unless I, bury it in meters of lead. And it's obviously not buried in meters of lead, right?
Yeah,
if it was, I couldn't interact with it.
Yeah.
So this is an assumption that observers have infinite power. So effectively that they're gods. And in quantum theory, that assumption is still kind of with us. And there's still this idea. I mean, another way to think of this is the assumption that we can talk about the state of the universe as a whole. Right? We can't observe the state of the universe as a whole. There are no observers of the universe. The universe is isolated. It doesn't interact with anything. So it's not being observed. But nonetheless, we write down formally things like, well, suppose the universe is in a separable state. I mean, no one can know that the universe is in a separable state. That's a theoretical stipulation only. And so that when one makes a theoretical stipulation like that, one's assuming what's called the God's eye perspective, or the view from nowhere, it's called sometimes by philosophers. And one has to be able to make assumptions like that to do physics. But they're completely non-empirical, right? They're theoretical, they're axiomatic, they're stipulative. They have nothing to do with observation. So that's a weaker form of this kind of infinite power assumption. But in quantum theory, there's still the assumption that some measurements can be made with infinite precision. There's just not the assumption that all measurements can be made simultaneously with infinite precision. So Heisenberg's uncertainty principle tells us we can't, for example, measure energy and time at the same instant, or position and momentum at the same instant, because the operators don't commute. But any kind of empirically reasonable form of either classical or quantum physics acknowledges that there are always degrees of freedom of the universe that can't be controlled. That my interactions with instruments in the laboratory are never free of interference caused by other observers, where I'm using the word observer here in a very loose kind of Wheeler sense of some other part of the universe. And Likewise, uh, I cannot control or even measure all of the effects of the rest of the universe on me at any time.
Mm.
So I can't keep track of the cosmic rays that are currently penetrating my brain and causing who knows what problems at the molecular level. So we we don't, as organisms, have the sort of capabilities that we're idealized as having in much of physics.
Yeah, it's really interesting to hear you say that. Yeah, and that's why I think one of the implications of like my understanding anyway of like the free energy principle and the sort of is it when you yeah, is it the holographic principle, this that notion of like the exchange of a like a qubit or of across the boundary, is it the holographic principle?
Yeah, it's in a sense a generalization of the original formulation of the holographic principle, which was formulated in black hole physics. Right.
Yeah.
Right. I mean, the holographic principle is really just a statement about information flow through boundaries.
Right. And that
You
it's
know,
limited essentially.
right, and that it's that in any for any finite system, uh, and hence for any physical carrier of information, uh, the holographic principle is based on the observation that a physical carrier of information, think of
Mm,
a photon, the simplest carrier of information we know about, um, has some finite energy.
mm,
And so uh, it it takes up some finite amount of room when it's crossing a boundary because it has some finite energy, so it has some finite wavelength, it has some finite frequency. It's got to be able to fit through a little piece of space. And
right.
the what Jacob Bekenstein argued back in the early '80s, I think it was, uh, working with um, results of Stephen Hawking's, was that the smallest space that a photon can wriggle through is 4 times the Planck area, so 4 times the Planck length squared, which is, of course, a tiny, tiny area, right? The Planck length is 10 to the minus 35 meters, so this is truly microscopic. Uh, but the fact that it's finite means that only some finite amount of information can get through any finite boundary. You can't have an infinite information flow through a finite boundary. So that's basically what the holographic principle says.
Yeah.
Uh, and one can think of it as applying to any interaction at all. Uh, and then it just says that a finite interaction uh, can't transfer an infinite amount of information.
Yeah.
And that when you say it that way, it makes perfect sense, right? Who would think that a finite interaction could give you an infinite amount of information, right? Uh, so it's one of those principles that sounds very arcane when it's first encountered. And the reason I think is historical, that it was originally formulated in this sort of arcane setting of the entropy of the horizon of a black hole. But in fact, it's a very simple principle and it's a very intuitive principle.
Yeah,
You know,
that's it. Yeah, it is, and it reminds me of I had this thought the other day actually when I was thinking about our upcoming conversation around the free energy. Because to me, anyway, I think it's one of the free energy principles, very intuitive, and yet at the same time, I don't think I would have ever come to it probably, and definitely not the mathematics involved in it because that's not really my sort of forte. But again, it's sort of similar. There's an intuitive sort of notion to it almost.
Yeah, I think that's very common in science, right? When
Yeah,
one comes at a complicated problem, and um, by digging and digging and digging, one comes up with what's in a sense a very simple and intuitive solution.
you're right.
And it's surprising, right?
Yeah,
It's like,
yeah.
oh, wait a
Almost,
minute.
yeah. Yeah.
That's not complicated.
Yeah, 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 yeah. Yeah, very
And
much
yeah,
so.
the math ends up being complicated, but in a sense, it's also complicated for historical reasons.
Right,
Because one, uh, Carl, for example, came at the free energy principle from this um, statistical formalism of networks of causal interactions.
right,
And when one actually tries to write that down in some explicit way, one turns to classical physics, and the kinds of expressions that one gets are fairly complicated.
mm,
And so you end up with a formal representation that, in some sense, is more complicated than it needs to be for purely historical reasons.
right, okay.
And so I mean, a lot of what's happening in the world of the free energy principle is different formulations of the same idea in different languages,
Oh, okay,
uh,
right.
with the aim of coming up with formulations in some language or other that are simple and very naturally applicable in some domain of interest,
Right, yeah.
that can be measured or manipulated in some particular way.
That's interesting. Yeah, because it's to be honest, it's often the case. I'll read a paper on like the FEP or something related to it, and I follow it and the language, and then it gets to the maths, and I'm like, oh gosh, But that's interesting to hear actually. Just coming back to though, just because for me it's a really interesting point. As I mentioned at the beginning, I'm quite sort of, whilst philosophy is not like a profession of mine, I think like yourself, I'm quite interested in it and the sort of like implications, some of, like perhaps like what, the findings and stuff from sort of physics and biology and how they sort of, there's like a kind of a symbiotic relationship, or there can be at least with philosophy and how we sort of make sense out of things. And I suppose what I'm saying is all of this is to say is that that kind of uh, before that sort of idea of a view was it a view from nowhere and that sort of like God's eye view. It sounds like you sort of hinted at you suspect there or you see it as being the case, but in my experience, I've often and I think this is what I quite liked about Wittgenstein, who I've heard you mention on the Chasing Consciousness podcast. I know that you've obviously have some familiarity with him because you used that sort of anecdote or sort of story he used about the sun rising and the sun falling.
Mm.
And I know Wittgenstein. I was thinking about this. Is that well, he was a think anyway. I say no. I think he was sort of against this kind of what I think is called sort of scientism. This idea that almost science can capture all the information and that we can have an understanding of everything. And I don't know if do you ever see this or have you ever sensed this in pockets of sort of science where it's not necessarily explicitly stated, or maybe it even is at sometimes where people go, oh, well, one day we'll know everything. But at times there's almost like that's kind of like the implicit sort of assumption. Have you ever have you ever noticed that?
Yeah, well, I think that informally that's very common. Um, you think of the phrase theory of everything. You take that
Right, right.
seriously, then
Yeah.
it really means the theory of everything. Um, Whereas when, say, a physicist actually uses it, they're really talking about, you know, a theory that manages to comprehend high energy physics and gravity at the same time.
Right, 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 right.
Um, so I mean, in a sense, one always needs to remember that physics is the simplest science in the world. I mean, it's the science that deals with phenomena stripped of as much complexity as possible. Uh, if you think about biology or psychology or sociology, you're dealing with much more complex systems than electrons.
Right, right.
Um, but this also has historical roots, which get back to this issue of thinking of scientists as gods. And there was the idea of sciences could be completely formalized in a completely consistent way and could, in some sense, be finished at some point.
Sorry,
And
that was an assumption.
yeah, that we could be done at some point. You could
Right,
actually learn everything,
right.
and one could develop this consistent body of knowledge that was actually complete. And uh, Godel showed in the late 20s, early 30s that this isn't possible, that it's not even logically possible, right? With his famous incompleteness theorems that basically said any body of knowledge that's at least as complicated as ordinary arithmetic cannot be described in a way that's both consistent and complete. And Gödel's an incredibly important mathematician or logician, because that's an incredibly important statement. It completely blew out of the water this traditional assumption that consistency and completeness and formalization could all be achieved simultaneously. And so not only is it not possible to know everything in science, we can't even know everything in arithmetic. That's basically what Gödel showed.
Right.
In the way that we thought we could, in the way that the whole Hilbert program of the early 20th century was based on.
Mm.
So, and I think it's interesting from a kind of cultural history point of view that we have, I think Gödel's paper was in 1928 or 1931 or something like that. The first Solvay conference where the great Bohr-Einstein debate really started is 1928. So quantum theory was developed in the mid 20s by Heisenberg and Schrodinger and Bohr and the rest of them. Right before that, in the teens, in art, we had the Dada movement, which kind of set out self-consciously to destroy these notions of everything being, of aesthetics being kind of categorizable completely. The traditional view of art. We had the birth of the modern novel, right, in that period between the wars.
Hmm.
And of course, we had the development of computer science, Turing and Church in 1936. And if you think of what Turing and Church did, and they were both very explicitly motivated by Gödel and by Gödel's results. But what they did in formulating the Turing machine and the lambda calculus, and recognizing then immediately that these were alternative ways of describing computation, what they did was demonstrate that computation is implementation independent. One can compute the same thing in many very different ways So you can use your laptop, you can use an abacus,
Mm-hmm.
you can use a Turing machine, you can use a lambda calculus, you can use a neural network, and you get the same answer.
Okay.
And that leads more or less immediately, right, when you think about observations or think about doing science, to the idea of the black box, which was well formulated by certainly the end of World War II by the early cyberneticists. And that was the idea that what's happening on the other side of the interface to the black box is implementation. Your observations of that interface are implementation independent. There's some computer over there, and it's giving you outputs when you give it inputs, and you don't know what's in there. You don't know what it
Right.
is. And it could be any one of an arbitrarily large number of different kinds of architectures. Church and Turing told us so. Right? So we have in the middle of the 20th century this whole complex of ideas that tell us that our ability to learn about the universe is very strongly and strictly limited.
Right. Yeah. Exactly. Yeah. Exactly. Yeah. Yeah.
That our observations can never, even in principle, get beyond the ambiguity of the world. That's implementation independence. And they can never yield theories that are both consistent and complete, assuming that the world has even the minimal complexity of ordinary arithmetic. That's Godel.
Right.
And quantum theory, in a sense, is just operationalizing that. It's just saying, yeah, you can't even measure position and momentum at the same time.
And can you hear me?
We have another freeze going on.
That's okay. Yeah.
Yeah.
You're back. Yeah. So you're saying yeah, I had a thought on it. It's gone, but yeah, you're saying around quantum sort of theory is a recognition of that. Yeah, and that's what I was going to say. And my sense is that, like you're saying there, is as humans, I don't think, or maybe even using the language of like the FEP and Bayesian sort of predictive processing and stuff, is like we don't like that. I don't think, that idea that we're limited, or to an extent. What I mean is I sometimes wonder this is like what is that drive to that sort of sense that we can or should know everything? I don't know. Is sorry, I'm pontificating, but following on from your point, so around Gödel and stuff, around these axioms, in a sense, then it's like, because I have a sort of a layman's understanding of Gödel's incompleteness theorems. Is essentially what he's saying is that like certain axioms we have, you can't define, you can't prove those axioms with the form of the system you're using, and therefore, in a sense, those axioms you almost have to, you just take them on almost like they're like just given. You just have to have them.
Yeah, well, that's what an axiom is by definition. It's something that one
True,
stipulates.
Yeah. Yes.
And what Gödel showed was that if one wants a set of axioms that give you all true statements in a domain at least as complicated as arithmetic, then that set of axioms will not be mutually consistent. So that set of axioms can also produce all false statements.
Right. Okay.
And if you want a set of axioms that you are able to prove that your axioms are mutually consistent, then they won't give you a complete theory. You won't be able to prove every true statement using those axioms. And of course, here, true has kind of a slippery meaning, right? Like, what do you mean by true? And one has to fall back on intuition here. Say, something that we think is true, or something that some formal model theory tells us ought to be true, or something that's true in some meta theory that sits on top of the theory that we're interested in. So one can wriggle out of these Godelian sorts of limitations by going to some higher level language and saying, so I can't prove it down here in my ordinary language, but I'm going to go to some more sophisticated language where I can prove it. But of course, Godel applies in that sophisticated language too, about the things that can be proved in that meta language or more sophisticated language. So, yeah, I think it's probably a delusion of self-awareness that we're able to understand everything. I think the fundamental delusion of self-awareness is we think we're able to understand ourselves, which of course we can't, right? All of these theorems, all of these limitations apply to us too.
Yes, and I heard you mention something like that before, and it made me question my own understanding of like the free energy principle and Markov blankets, because I think you once said like regarding that there around this, we can't even fully understand ourselves. Is that around the fact that we can only infer our internal states through almost like our perceptual interface, or that the sort of Markov blanket?
Yeah, we're constantly trying to observe ourselves. So what does we here mean? Well, if I'm a system and I'm observing myself, if I say I'm observing myself, what I'm really saying is that there's some part of me that's observing the rest of me. So it's using some boundary to make those observations. And so it's subject to exactly the same sort of limits that we've been talking about all along. If you can put this more formally in kind of computational terms, is if you have a system that consists of some processor and some meta processor that looks at what the processor is doing, then the meta processor interacts with the processor through some API, right? Some interface. And it can't completely determine what the processor is doing by making measurements with that interface. And all of these results have to do with the fact that one can't get an infinite amount of information through a finite boundary.
Yes. Yeah, and okay, yeah, no, just because there's a couple of other topics I really wanted to talk to you about, sort of just kind of like sort of moving on in a way. I wanted to ask you about kind of minimal physicalism. And in a way, sort of, I suppose, yeah, things like space-time. Okay, so maybe start with, if it's okay, could you describe what minimal physicalism? Is that right?
Yeah. Well, this I mean, you're referring to a paper that Jim Glazberg and Mike Levin and I wrote a few years ago in Neuroscience of Consciousness, where we talked about minimal physicalism. And what we're trying to do in that paper is develop a formal representation of perception and action that applies to any sort of organism
Mm-hmm.
or any sort of physical system.
Mm-hmm.
But the real motivation there was, the great debate in biology or ethology about what systems out there are cognitive, what systems are conscious. And we actually start that paper by quoting a very nice article that was in Current Biology in 2020 or 2019 or something like that, where a large number of comparative biologists are talking about, what systems are count as cognitive. And there's a lot of
Right.
disagreement. I mean, that's why they published the article.
Right.
And so we were largely motivated by how can we describe what, in some sense, very simple organisms like bacteria are doing, what they're able to learn about their environments, how they're able to act on their environments, how much memory of what they've done already they have, which of course is tied up in learning. You can't learn anything unless you have some sort of memory resource to store what you've learned in. So how do we think of these very simple systems in cognitive terms, as perceptual and active agents? And of course, we turn immediately to the FEP and the idea of active inference, because that's what that language is about. And you mentioned space-time. A very natural question, which we bring up in that paper, and of course we don't answer it, is how do we talk about the sense of time for any arbitrary agent? So we all have an intuitive sense of time, but is that really necessary? And clearly, to have a sense of time, you have to have a memory. If you're going to do any planning, you have to have a sense of time, and you have to have a memory so you can keep track of what you've been planning with. But what's the minimal sense of time? And we know that, for example, bacteria have circadian rhythms, and that the genetics of that circadian system go way back. It's highly conserved, seen across organisms. So there are clocks built into biology from the very beginning. And we can ask that same question about space. Right? We naturally organize our experience in spatial terms. We see objects as embedded in this container that we call space. But where does that come from? And do all organisms have it? Right? When we look at the behavior of other mammals or birds or reptiles and other vertebrates, they certainly appear to have this sense of space. When we think of the behavior of, say, cephalopods like octopus, they certainly seem to have a sense of space. But how far down does that go in the phylogenetic tree? Do plants have a sense of space? Do, say, sponges have a sense of space, et cetera? How would we find that out? And we wanted to be able to raise all of those questions in a consistent way within one formal framework. And the active inference framework gives us that opportunity. We can ask about those sorts of things in a simple, consistent way. So, does the generative model that's deployed by, say, a paramecium include a sense of space? And is it 2 dimensions or 1 dimension or 3 dimensions? And you can have any number of dimensions of a sense of space. And above 3, things become very complicated, and things that work in 3 dimensions don't work in higher dimensions, just of space. So that was our objective. And we wanted just the minimal set of assumptions we needed to be able to ask those questions. And the FEP formalism naturally gives us that minimal set of assumptions. So it's really a paper about how we can use the FEP to ask questions across biology in a consistent way.
Yeah, and you use the word cognition quite a lot there. Though I think I've heard other people, maybe a conversation you had, where minimal physicalism was brought up in the context of consciousness and perhaps what it's like to be a certain system. And that perhaps, I think, because you speak around, I'm not sure like how dear you hold it to your heart as perhaps say some other people do, like, you know, Philip Goff and people like that. And I know you sort of like, I don't know if sort of, how do you say, kind of tongue-in-cheek refer to the proxy war. I suppose what I'm saying is that I think you refer to yourself as somewhat of a panpsychist. And I'm just curious, so you've spoken about cognition and the FEP with regards to minimal physicalism and at different sort of, where do you draw the line and stuff like that, and what's it like to be a certain system? How does that relate to, does that relate to consciousness in your mind then? Or
no, I characterize myself as a pretty unapologetic panpsychist. I mean,
okay.
I think this whole notion of drawing a line someplace and saying everything on the other side of that line isn't conscious by kind of stipulation, I think that's silly. It's certainly not empirical. I mean, we have no evidence to go on here. All we have essentially is analogy, both informal sorts of analogies. You know, you interact with your pets and you think, oh, well, they obviously see me. They must be conscious.
Sure.
They're behaving in an interesting way. They must be conscious. I don't think anyone thinks their dog is a zombie.
Yeah,
Not serious. And then we have formal analogies, right? The FEP provides us with a bunch of formal analogies. It says, look, all systems are Bayesian agents. And they may be really minimal Bayesian agents, but all systems are interacting with their environments on the basis of some model.
And therefore it's something to like it is to be that system.
Well, it says if there's something that it's like to be you, then why not at least entertain the possibility that it's something to be like that other system?
Yeah.
And then there are other results that come from other disciplines. So, for example, in physics, we have the Conway-Kochen theorem by John Conway and Simon Kochen that was proved in the mid 2000s, and it's the title of the paper was the free will theorem, and basically what it says is that if you have some experimental setting where you have an experimenter and you have some system, let's say the system's an electron, then if the experimenter has free choice in how to do the experiment, then the electron has exactly the same kind of free choice in how to respond to the experiment. And the kind of free choice is very strictly defined. The choice is free to the extent that it's not determined by all of the events in the past light cone of whatever system we're talking about. So if the experimenter's choice of how to adjust the dials on the instruments is not determined by the experimenter's past back to the beginning of the universe, then the electron's response to that experiment is not determined by the electron's past going back to the beginning of the universe.
Right.
And it's basically a simple consistency argument. And indeed, if one thinks in purely quantum theoretic terms, any system has what's called free choice of basis, which basically means free choice of semantics. of how it's going to measure its environment, what language it's going to use to measure its environment.
Mm-hmm.
And if you have some system and its choice of basis for interacting with its environment is completely determined by its environment, then it and its environment are entangled. So it's not a separate system.
Okay.
So separability goes with free choice. And again, this very strict sense. And so we have these formal results that deeply challenge the notion of classical local determinism,
Mm-hmm.
which is what we were talking about earlier when we were talking about, determining that my interactions with this thing
Sure.
are that this thing is completely isolated from the rest of the universe and only I am determining what it does. And we don't have the power to do that. And nothing has the power to do that. No finite system has the power to do that. And that's what these theorems are really saying. That this idea we have, and that's deeply embedded in the worldview of classical physics, though it's not deeply embedded in the formalism of classical physics, that determinism can be both complete and local, is wrong.
Mm-hmm.
That it's actually inconsistent with other things that we want to be true. So that was a bit of a digression and an aside, but I think that these ways of thinking motivate us to be a little bit more liberal
Right.
in how we think about experience and how we think about how other systems interact with the world, and whether we grant that their interactions with the world can be characterized in terms of experience.
Sure. Yeah, I think
And
that's what. Oh, sorry.
and I think that that's all that people like Galen Strawson and Philip Goff are really pointing to when they talk about there being no place to draw a line. They're really just saying, oh, look, there's not really a big difference between us and other things. So let's be a little bit more liberal when we describe them or think about them.
Yes, definitely. And I think hearing you say that, and when I've heard you mention it before, I think write about it maybe, it's a bit more deflationary and kind of, yeah, sort of makes consciousness perhaps less sort of special or sort of, yeah, basically, which is kind of interesting to think about. It just to I'm curious around this idea of the kind of like consciousness as, how would you say, substrate or not? Okay, and what I mean, I suppose my sense is that your approach is more around consciousness is a given, but we can't necessarily understand how that given comes into being, albeit certain systems when they have enough, I don't know, informational sort of exchange or something with an environment, perhaps it is like something to be that system, right? Something like that. But then there are people like Don Hoffman, who my sense is it's more almost like consciousness is a substrate. So how do you hear that, and how do you when you read? I'm sure you're somewhat familiar with Don's. I know you are with his interface and his evolutionary sort of, because you co-author papers with him in terms of the evolutionary sort of interface. Fitness beats what is it? Fitness beats truth theorem and stuff. But in terms of his sort of approach to consciousness, which appears almost a bit like of an idealism, how do you make sense out of it, and do you see it differently? Yeah.
Well, I guess I would say that I don't see the classical distinction between physicalism or materialism or whatever you want to call it, and idealism as being any more very useful. I mean, I think that the approaches like the FEP or even Don's conscious agent theory give us a language that's better than this traditional language for talking about these issues.
Yeah.
And I mean, I would characterize Don's approach and any panpsychist approach as basically saying that experience or awareness, and I like those terms better than consciousness because
Yes.
they're less loaded with baggage in my view. Is fundamental. You know, it's a fundamental assumption that we make when we're doing science. And what that means is that the interesting question is the question, conscious of what, or aware of what? What am I able to be aware of? And what is some system that I'm interested in, like E. coli, able to be aware of? You know, what is a fish able to be aware of? And I think when one asks the question that way, it reorients to not only in a more empirical direction, but also to, what's the word I want to use here? Also to an orientation that is more, shall we say, empathetic. What are the sorts of experiences that this system is actually able to have? Not what are the experiences that well, one can ask, what are the experiences that it's having right now in some setting? But I think the more interesting question is, what are the experiences that it's able to have? And it may be that it's only able to have very simple kinds of experiences. And I mean, this gets back to the kind of godlike bias. We tend to think of ourselves as able to experience anything. But that assumption is kind of crazy, right? Why would we assume that?
Yeah.
There may be systems that are able to have experiences completely unlike ours. And we may be able to have experiences completely unlike theirs. So I think it by recasting the question that way, it makes one think differently about what one is doing in biology or psychology or anything else.
Yeah. And it makes me think, I think you might have spoken about it briefly, and I listened to it a couple of years ago when you spoke with Kevin, Mike and Carl on the Theories of Everything podcast. And I think, I don't know why it comes to mind now, but I think you must have spoke about it. With all of that, then in a way, not saying, but I suppose it's possible that there are systems at larger scale than we are, and that in a sense that we maybe can even perceive or understand, which have an understanding of themselves, given if we go up from, look down sort of below ourselves almost, in that I don't think a neuron is aware of the fact that if there is something it is like to be a neuron, hypothetically, I don't think it knows that it's somehow coupled to or furnishing me this awareness of me at this level. And it kind of makes you think, well, where could it stop? Maybe, you know.
Yeah, no, I think that's a very productive way to think. I think it's a very good question to ask.
Yeah, it's interesting. But yeah, and it is, and I think it's interesting because I think I don't know, some people might go, oh, that's just woo-woo, but actually why is it? You know, I don't think it is necessarily. Yeah, and also just because I see the time, I'm just curious to get your thoughts on Well, I suppose I was going to say Federico Fajim, I think, but you probably somewhat agree with a lot of his work. But he's also spoken about sort of AI and the sort of difference between kind of humans and computers in a way, and this sort of semantic versus symbolic bridge. And that I think his approach is that computers kind of, how would you say, can never have a semantics almost. Perhaps you don't even need to consider what I mentioned there about Federico, but just with the AI, I know you wrote a paper recently, and I couldn't actually access it from the computer I was using at the time. But I think it was around how much do we want AI to be like us. But do you want, or I don't want to, do you think it makes sense to consider that AI could have an experience, let's say? Firstly, I'll just ask you, what are your thoughts with regards to that?
Well, I think there are two ways to pose that question. One is to think of an actual implemented AI system. So a robot or a computer that's running some program or something like that. And the other way to ask that question is in some completely abstract way. So
Okay.
let's take the abstract way first, right? A program is just a pile of mathematics living in Plato's heaven or something like that. It's no different from any other pile of mathematics in any fundamental sense. And unimplemented, so not even implemented in someone's brain, that's just an abstraction.
Right.
And so there's no point in even asking, does this thing have any experience? It's not even a physical system, right? It's just a bunch of descriptive language, right? My old advisor, my PhD advisor, Rob Cummins, used to say, look, always think of computers as things that grew up in your garden. And what you're trying to do is understand their behavior. And when you're programming them, you're giving them inputs. You're giving them a bunch of text.
Mm-hmm.
A program is just a bunch of text.
Mm-hmm.
And you're saying, okay, computer, here's a bunch of text. What are you going to do with it? And then it does something. And you try to figure out why. So from his point of view, dealing with computers is basically like dealing with organisms. You have to think of your interactions with them as experiments. And if you think in that way, that not that this is a device that I completely understand and I can perfectly predict how it will behave. Instead of thinking that way, which is a very abstract way to think, you think about it as this is a physical system that behaves like any other physical system. And it encodes a potentially infinite amount of information. And I can't access an infinite amount of information. I don't know an infinite amount about my laptop. I know a small finite amount about my laptop. Someone like Federico, who designs chips, knows a whole lot more about my laptop. But at the end of the day, it's a physical system. So it's embedded in some environment that it's interacting with all the time. And I can give it inputs and I can get outputs from it, which means I can act on it and it can act on me. And if I want to think about it as a cognitive agent or an active inference agent, then I do so using exactly the same kinds of arithmetic and concepts that I use if I'm interacting with E. coli or a tree or another person. The formalism is the same. So if one thinks that way, then one is much more likely, I think, to be, shall we say, free to entertain the idea that some artificial system is a cognitive system or an experiencing agent, and to actually strongly question the meaning of the term artificial. I mean, we make these things. But we make them in much the same way that we make clay pots, right? We get a bunch of stuff from the world, and it's stuff that we can characterize, but we're a little bit crazy if we claim that we completely understand it. And we mush it together in various ways. And when we're making computers, we do this in a very sophisticated way. But it's still stuff. It's still material. It's still, at the end of the day, a quantum system that we're manipulating. And so I think we have to think of ourselves as agents who are interacting with parts of the world, parts of our worlds, that are, in a sense, given to us. And we're using power that may be considerable, but it's not infinite, to mold these degrees of freedom of the world to behave in a certain way, right? We're active inference agents. What we do is we operate in our environments to try to get our environments to behave in a way that we like. But we're not gods. We're not capable of exactly determining what those systems are going to do. They still have some freedom.
Yeah. Yeah, interesting. It makes sense what you said. Yeah, it's interesting because people have sort of, well, like you're aware, sort of very kind of, and it's sort of one of the conversations, I suppose, in the zeitgeist, sort of like, what can AI be conscious? But yeah, where I see the time, and yeah, it's I think it's a nice place to sort of finish.
Well, thank you. This has been great. Good
Yeah,
conversation.
yeah, I really enjoyed it. Yeah, kind of covered a fair bit, and yeah, I've got a lot from it. So yeah, thanks very much, Chris. And for those, yeah, interested in your work, I will. Well, I'll put the link because you've got a website which lists you actually sort of list your papers on, and also links to you've done several, well, yeah, many talks and podcasts which I can link some to, and as well which I found quite. I haven't listened to all of it, but I listened to a few of them. It's quite illuminating. Was the physics as information processing lectures. Yeah,
Yeah,
and
those are all linked on my site. So yeah, if you just link to my site and then link to whatever that's on it that you want, and there is a preprint now of that How Much Like Us paper on the website, so you can get it.
oh, is it? Oh, okay, right. Yeah, and I don't know what your plans are, whether it's to just sort of like just relax in France forever, or to carry on doing work. But assuming you do carry on, I'll continue to follow your work.
Okay. Well, thank you.
All right, Chris, thanks very much.
Okay. Cheers. Have a good evening.
Yeah, you too. Bye.